In this part 2, we aim at talking about free bordering minimal surfaces into Euclidean balls. These surfaces are very similar to minimal surfaces into spheres. And I will not give a very long explanation of on these surfaces, because you can find on this channel a video by Martin Lee, which is very complete on the subject. But here I would like to focus on the link between these surfaces and eigenvalues of operators. So these pictures were computed by Kao, Hosting, and Ude by shape optimization of Steklov eigenvalues. And they correspond to free bordering minimal surfaces into Euclidean balls. They are of genus 0. And you see that in these examples, you may have immersions. In fact, when you maximize the first Steklov eigenvalue, you must have embedded surfaces. But for higher eigenvalues, it's not clear. And in fact, you can find minimal immersions which are not embedded. So let me focus on definitions. First, in the closed case, we say that something is an immersion if we have a tangent plane at each point on the image. And we denote the set of immersion as follows. Take I sigma M, where M is the target manifold. It is the Euclidean space or the sphere in our case. So definition, we say that an immersion is isometric if the pullback of the Euclidean metric is the Riemannian metric. It is conformal if the pullback is conformal to the Riemannian metric G. That is that you have a positive, smooth positive function as a multiple of G. Phi is a minimal immersion if it is a critical point of the area of the image of the immersion. And we say that it is harmonic if it is a critical point of the Dirichlet energy. So we prefer to focus on the Dirichlet, we often prefer to focus on the Dirichlet energy because it's more convenient for variational problems. And we have this inequality, which is very simple to prove, with equality if and only if phi is conformal. And then if you want to do a rational principle, a minimization of the area to find minimal surfaces, it's more convenient to minimize this Dirichlet energy and to notice that if you have a minimizer, then it is also conformal. So harmonic plus conformal gives you that you are a minimal immersion. So let me give the link between minimal immersions and eigenvalues of the Laplace operator. There is this classical theorem by Takahashi, which tells you that if you take a map, which is an isometric immersion and satisfies the eigenfunction equation, so eigenfunction with respect to some eigenvalue lambda, then we must have that this map goes into a sphere and that it is a minimal isometric immersion. In fact, I will not give the proof of this theorem, that I would just like you to focus on these simple facts. If you take a conformal immersion, that is, for instance, in some conformal chart that phi x squared is equal to phi y squared and phi x and phi y are orthogonal, it is well known that phi is a minimal immersion if and only if it is a harmonic map, because we assume that phi is conformal. If and only if it is the Euler-Lagrange equation associated to harmonic map, the Laplacian is parallel to phi if and only if the Laplacian of phi is equal to 2 phi, that is that phi, the coordinates of phi are eigenfunctions associated to the eigenvalue 2 for some new metric defined by a conformal factor times the previous metric. And the conformal factor here is just the density of energy of the harmonic map. So we have a characterization of minimal immersions by eigenvalues and eigenfunctions. In the 90s, Nadirashvili noticed, and El-Sophie and Ilias for higher eigenvalues, that if we look for critical metrics for Laplace eigenvalues, then the Euler-Lagrange equation associated to this criticality gives you minimal immersions into some spheres. So I will give more details in the next sections about this, this subject, but you can focus on this idea. In order to build minimal surfaces, you can work on optimization of eigenvalues. And for instance, if you maximize this functional, then you have a maximal metric and you get minimal immersion into subspheres. In the free boundary case, we have the same kind of property. If you take phi a conformal immersion such that the boundary is sent into a sphere, then phi is a free boundary minimal immersion. That is that it is a critical point of the area in the set of immersions such that the boundary is sent into sphere. So the boundary can move freely in the sphere, and you want to look for critical points of the area for it. So as before, you can define critical point for the energy, always on the same set of surfaces lying such that the boundary lies in the sphere. And because we assume conformal, it is equivalent. And then we notice that being a free harmonic map gives you as a Euler-Lagrange equation this system of equation. So it is harmonic in the surface, and the outward pointing normal of phi is parallel to phi on the boundary. This means that phi meets the boundary orthogonally. Phi meets the sphere orthogonally. And this is true if and only if we have that phi is in fact, the coordinate of phi are in fact Steklov eigenfunctions associated to some metric which is conformal to the previous one, where the conformal factor, as before, is defined as a density of energy with respect to the map. So what matters here is the density of energy on the boundary, and you can extend by what you like in the interior, because it is conformal invariant. This equation is conformal invariant here inside the surface. Then, thanks to this remark, Fraser and Shane noticed the same thing as Nadirashvili. If you take some metric which is critical for Steklov eigenvalues, then you get free boundary minimal immersions. So I'll give a more detailed explanation of this theorem in the next part, but I would like to finish with many results of construction of free boundary minimal surfaces. So if we start with an oriented surface, because it is simpler to explain this, surfaces of genus gamma with M boundary components. I give you all the results I know about this problem. First, if we maximize the first Tekloff eigenvalue on disks, you only get the flat disk. And the proof of this result is exactly the same as Hersh's theorem in the closed case. And the minimal immersion you get is just the identity map between the flat disk and flat disk. Then Fraser and Shane proved by shaped optimization of the first Tekloff eigenvalue that the critical catenoid, which is a free boundary minimal surface, maximizes this sigma 1. And they also proved that it is the only maximizer. Then we have works on genus 0 surfaces. So Fraser and Shane prove that if you maximize the first Tekloff eigenvalue, they must be into a Euclidean 3-dimensional ball and embedded. And by variational method, we are able to build free boundary minimal surfaces. And Cao, Hosting, and Ude computed numerically these surfaces of genus 0. Then you have other constructions which do not depend on eigenvalues. Constructions by Foya-Packard-Zolotareva for low genus and large M, and construction by Ketover, Kapoulias and Lee, Kapoulias-Vigel, which is essentially desingularization of union of equatorial disks or union of catenoids and disks. And you get surfaces with large genus. And that's why the boundary components are only 3 and 1. And the last result is by Carlotto, Franz, and Schuss. They prove existence of free boundary minimal surfaces for any genuses, but the boundary is connected. So the new result I'm going to talk about is a result with Henrik Mathiesen. We are able to prove by variational methods on Tekloff eigenvalues that there are free boundary minimal surfaces for any finite topology. So we lose that the target manifold is a 3-dimensional manifold. It is the case in genus 0 surfaces, but not the case here. And they are not embedded anymore. So in the next section, I will give more detail on shape optimization of Tekloff eigenvalues in order to build these surfaces.